Hi everybody. Today's section is on 11.4, the comparison tests. That's right, it is pluralized because we are going to be learning two different tests in this section. So without further ado, let's talk about the first theorem, which is called the comparison test. Which I like to abbreviate CT. Okay, so here are the conditions of the test. We need to always be really careful that we read the conditions carefully. So this is a test that allows us to compare two different series. So let's suppose that AN and BN are both positive series. Okay, I did not put n equals 1 to infinity on these series just because it doesn't, just assume that it's there. I'm just trying to save on writing here. They're both positive series. That means that every term is positive. Okay. Suppose that AN is less than or equal to BN eventually. Or let me write it this way, from some point on. What we're saying is it doesn't have to be smaller than it the entire time, but from some point on, maybe from the fifth term on or something like that. Okay? What can we conclude? Okay? Then, first, if AN diverges, then BN also diverges. Okay, that's the first thing. Okay, let's before I write down the second conclusion here, let's think about this. Okay, what I'm saying is that remember, AN is the smaller series here. So what we're saying here is if the smaller series diverges, then the bigger series also diverges. And the next one, what happens if the smaller series converges? That wouldn't tell us anything, but what if the bigger series converges? Then the smaller series also converges. Okay, so this is the theorem. Okay, the theorem says that if you have two positive series and one of them is smaller than the other from some point on, then that means that the bigger one diverging tells you that the smaller one does also, or if the bigger one converges, then that tells you that the smaller one must converge also. Okay? All right. So this is an extremely useful series. One thing I should say is the hardest part here. Let me just say note. Choosing a series to compare yours to can take practice. Okay, so try to choose a series The whole point is to try to choose one that's related to yours, but easier to study. Okay, so this is my little tip here. So let's go ahead and try an example. This is going to be number 1. So study the series. Our series is going to be 7 over 5n to the 4th plus 3n cubed plus 4n plus 1. Now, you could see that this is a very complicated series, right? You've got this giant 4th degree polynomial underneath, and, it's hard to study this directly. So what do? Well, what we can do is just sort of in our minds, I want you to think about the part of this that does matter, okay? The part of this that really matters, that think about what happens when n gets really large. The terms that are going to dominate are as follows, right? When n gets large, the 4th power on the bottom will dominate. So really, as we get big, that's all that's going to matter, right? Okay? So what I'm going to do is I'm going to choose another series. So let's let, if this whole thing we call an, then let's let bn be as follows: 7 over 5n to the 4th. Okay, so this is the series that I'm going to study. Now we need to compare them. So what can we say about this series and what can we say about this and this? Which one is bigger? Well, I want you to think about it. The one on the right has a larger denominator, so therefore it must be smaller. So this guy is bigger. Okay, so this is true. And this is actually true for all n, so I'll just write that down. But what do we know about this series? The whole point is that we want to study this series because it is easier. Do we know if it converges or not? Well, the trick is that if you think back to what we learned in the last section, if you pull out the 7/5, we notice that this guy right here is a p-series. Look back at section 11.3 to remind yourself of our p-series studies. You have to make sure that you understand that before we go on to this section, okay? So this is a p-series with p equal to 4, which is greater than 1. What does that mean? This implies that this series converges. So what can we conclude? We can conclude that by the comparison test, this series also converges. And we're done. Okay. Again, we have to be careful here because the comparison test, you have to be careful because the direction matters here, right? It mattered, for example, that this guy was larger, right? It was larger and the larger guy converged, so that's why the smaller guy had to converge also. Okay, but if that larger guy had diverged, we would have gained no information. Okay. All right. So let me just write that as a be careful on the next line here. So be careful when using CT if AN is less than or equal to BN and either the smaller guy converges or the bigger guy diverges, the test tells us nothing. Find a different series to compare yours to, or try a different test. Okay, this is extremely important. I'm going to put little stars here, okay? The comparison test is very particular. Make sure that after you do you figure out whether yours is bigger or smaller, that it goes in the right direction. Otherwise, you are making a conclusion that is not justified. Okay. I'm going to try a different one. So let's do number 2. This series is going to be ln of k over k. And we're going from 1 to infinity. We don't even actually need to start at 1. We can actually start at 2, right? Why? Because ln of 1 is 0, so the first term wouldn't contribute anything anyway, right? So let's just go ahead and start it at 2. Now, this problem, I want to point out that the integral test would work, so let me just say the integral test would work, but we will use the comparison test instead. So what are we going to let Bn equal? This is always the tricky part. So we want something that's easy to compare this series to. So I'm going to let Bn just equal, or how about we use k because the problem isn't stated in terms of k's. So let's let Bk equal 1 over k. How do you compare ln of k over k to 1 over k? Which one is bigger? Well, of course, natural log grows bigger than 1, right? Everywhere except when k is 1. So we could say that this is true for all k that are at least or that are bigger than 1. In other words, from some point on, this is true. What do you know about this series? This series, remember, it diverges. You could say it is harmonic. Remember, we showed that the series 1 over n diverges. You're allowed to just say that because it's a fact that we cite all the time. Or another alternative justification is you could say it's a p-series with p equal to 1, which is less than or equal to 1, right? Because that's really a 1 right there. It's k to the first power. If you write either one of those down, that's totally okay. All right, now, coming back to our problem, are we done? Well, think about it. We found a smaller series, and we just showed that the smaller series diverges. So we can now conclude by the comparison test this guy also diverges. Okay. Okay. So I want to illustrate a slight weakness with this test. Let me go ahead and do another example, and we're going to see a problem. So example 3. So study the series. Let me actually start this series at 2. Okay, so a natural thing to do here would be to consider that our Bn. So let's let Bn equal 1 over 5 to the n. Let's go ahead and compare these two. Okay, how do we compare 1 over 5 to the n minus 1 and 1 over 5 to the n? Well, I'm hoping it's clear that the one on the right has a larger denominator, therefore it is smaller. So this guy is bigger. Now let's look at 1 over 5 to the n. What kind of series is that? Well, this is clearly a geometric series. What's the first term? The first term is 1 over 25, and the ratio is equal to 1/5, right? Because every time you multiply it by 1/5. And the absolute value of 1/5, which is 1/5, is less than 1. So this means that this series converges. So then what does the comparison test tell us? I hope you didn't say that the other guy converges too, because we have a problem, right? We just showed that the smaller guy converges. So what can we say about the bigger guy? We can say nothing. So let me just say the comparison test tells us nothing. So we have a problem, right? The problem here is that this test is not working only because there's a minus sign there, which is really silly, right? Because we know that in the long run, the two series are pretty much going to look identical, because that minus 1 is not going to matter when things get really big. And so we need another test to deal with the issue. So we will come back to this. So we're going to learn another test. So this theorem is called the limit comparison test. Which I'm going to abbreviate LCT. Okay? So we're going to start with, suppose AN and BN are positive series. Now, this one does not depend on one being bigger or smaller than the other. Okay? So, suppose that the limit as n goes to infinity of, here's what you're going to look at. You're going to divide the terms of one series by the terms of the other series. And we want to see what this equals. So suppose this limit is equal to some number that is greater than 0 and finite. Okay. So what we're saying is it can't be so small that it's 0, and it can't be so big that it's infinity. It's got to be some number in between, right? It might equal 20, it might equal 13, it might equal 1/5. It could be any positive number. So what does this mean? If dividing them gives you this limit, then that actually means that in the long run, AN is just some number times BN. In other words, here's what the theorem tells us. Then AN and BN behave the same. What does it mean they behave the same? This means they either both converge or both diverge. Okay? So this is an extremely useful theorem. I would say this test is even more useful than the comparison test, although there are situations where limit comparison doesn't work and the comparison test does work. So you really do need to know both. But I would say that this one comes up more often. Okay? So let me give you a hint here before we begin, or a tip. So tip 1 is the limit comparison test is best used when your series is a rational expression or any quotient of similar terms. Now you notice for this one you are still going to have to choose a second series Bn. So tip 2, this is going to be similar to the tip I gave for the comparison test. Let Bn equal the ratio of the dominating terms. Okay, the ratio of the dominating terms. Okay, so these are my 2 tips here. Let me go ahead and come back to example 3. And I'm going to show you how we can use this test to help finish the problem that we couldn't do earlier. Okay, so back to problem 3. Remember, we were looking at this series, right? So we're going to do what we did before. Remember, this guy, we usually call this guy AN. And I'm going to let BN be 1 over 5 to the n. Again, these are the terms that dominate, right? The minus 1 is not going to change anything. So, what is the limit as n goes to infinity of AN over BN? So you divide one series by the other. So this is going to be the limit as n goes to infinity of AN over BN. So that's times 5 to the n over 1. So this is equal to the limit as n goes to infinity of 5 to the n over 5 to the n minus 1. So how do we take this limit? Well, what I'm going to do is I'm going to use the trick that we use in Calc 1 to do a limit like this, because otherwise we get infinity over infinity. I'm going to divide top and bottom by 5 to the n. Yes, you can use L'Hopital, but that's going to actually make things much more complicated, because we can actually just use this trick to simplify things. We're going to do the limit as n goes to infinity. The top becomes 1, and over here we get, we get 1 minus 1 over 5 to the n. And if you send n to infinity, this guy goes to 0, so this entire limit just equals 1. Is this good? Yes, it is, because if you come back here, we said that as long as you get something that is greater than 0 and finite, then they behave the same. So I'm going to say that this is greater than 0 and finite. So by the limit comparison test, this series and this series behave similarly. Now, I'm not done yet, right? I still need to say what Bn does. But we already said that before. Let me just write it down. This guy converges. Remember, it is geometric with the ratio equal to 1/5. Right? Come back here, and remember, we already said that it converged, okay? I'm just reusing the information we already did, okay? So what do we know? This means that our series also converges. So we're done. Okay, so we actually used a couple of facts, right? We used LCT, we used geometric, we used all that stuff. So this kind of shows you the strength of this test. Sometimes the comparison test doesn't work, but this test does work. I'm going to do a couple more examples to demonstrate this test. So study the series. Pretty complicated looking, right? We're about to learn the beauty of the limit comparison test. It's going to make our life a lot easier. So what is the trick? Well, again, let's start by calling this is an. And what are we going to let bn equal? Think about this series and the terms that dominate, okay? On the top, the term that dominates is the n cubed term. And on the bottom, the term that dominates is the n to the 7th term. Okay? So I'm going to make my bn equal to n cubed over cube root of n to the 7th, right? What I'm trying to do essentially is look at just the terms that dominate. When things get really big, all that's going to matter is that term and that term, right? So I'm going to let bn equal n cubed over cube root of n to the 7th. Okay? Let's begin with the limit. We want to show that they are going to behave similarly, so we're going to use LCT right now. What's the limit as n goes to infinity of an over bn? Now, when you do a complicated limit like this, I'm going to show you something. So start by writing an over bn. Here's an. And then bn is this, right? I divided, so I multiplied by the reciprocal. But here's the trick. The trick is, if you notice, these two are compatible, and these two are compatible with each other, right? Because they've both got cube roots and stuff. So what I'm going to actually do is rewrite my limit this way. Why did I do that? Because now I can do these two simpler limits, and this one I'm going to divide top and bottom by n cubed, and this one I'm going to divide top and bottom by the cube root of n to the 7th. So let me show you what we get on this first limit. We get 6 minus 3 over n plus 5 over n cubed. The bottom we get 1. Over here we get 1 over the cube root of 2 over n to the 7th plus 4. So if we send n to infinity, that guy goes to 0, that guy goes to 0, this guy goes to 0. What do we end up with? We end up with 6 over the cube root of 4. But that's a positive number, and it's finite. So what did we just conclude? Remember, the whole point of doing this was because we wanted to study this guy instead, right? This guy is easier to study. And we just concluded that they must behave similarly, right? So let me write that down. By the limit comparison test, an and bn behave similarly. So now let's look at bn. Presumably it should be easier, right? Remember, bn is n cubed over cube root of n to the 7th. So this is the same as n cubed over n to the 7/3. 9/3 minus 7/3, this is actually 1 over n to the negative 2/3. Sorry, let me erase this here because I'm looking at just Bn, right? So what can we say about this? This guy is a p-series with p equals negative 2/3, which is certainly less than or equal to 1. So what does this mean? This means that Bn diverges. So this implies that An also diverges. And we're done. You could see that doing problems like this is a little bit different than the math you're used to doing, right? Because we're presenting an argument here, right? And we're logically, it's sort of like a proof, right? We are proving each step. We're justifying our argument. In the end, it's not your answer that matters, right? I mean, if you were to take a guess, you could have a 50-50 shot of guessing whether it converges or diverges. Okay, if you get the right answer but your work is wrong, I would give 0 credit for that, okay? The important thing here is that you understand how these tests work and you're able to apply them correctly. It isn't about guessing the right answer. Okay, that was a cool problem. I want to do one more. And this one's going to be trickier. So this is going to be number 5. We're going to study that series, n plus 4 to the n divided by n plus 6 to the n. Okay, so what are we going to study using the limit comparison test, right? We need to actually figure out what to compare it to. What's going to dominate here? Let's first call this whole thing an, and I'm going to say let Bn equal. Well, we should know, it's a good thing to know just in general, that exponentials always dominate polynomials. In other words, these two guys are going to dominate the expression. So we're going to let Bn equal 4 to the n over 6 to the n. So we're going to use the limit comparison test. We're going to do the limit as n goes to infinity of an over bn, right? This is equal to the limit as n goes to infinity of n plus 4 to the n over n plus 6 to the n times 6 to the n over 4 to the n. So I'm going to do what I did in the last problem. I'm going to write this as a product of two limits, and I'm going to separate it into the ones that are related to each other that are easier to calculate. The first one is n plus 4 to the n over 4 to the n. The second one is 6 to the n over n plus 6 to the n. Okay? So on this one, I'm going to divide everything by 4 to the n on top and 4 to the n on the bottom. On this one, I'm going to divide by 6 to the n and divide by 6 to the n. So we end up with, first limit is n over 4 to the n plus 1 over 1. And here we get 1 over n over 6 to the n plus 1. Now the problem is that when you try to do these limits, we have to know what the limit is of n divided by an exponential. So let's do that off to the side, okay? So I'm going to do, for example, this limit off to the side. What is the limit as n goes to infinity of n over 4 to the n? Well, if I get infinity over infinity, I'm going to use L'Hopital's rule. So if I use L'Hopital's rule, I end up with the limit as n goes to infinity of 1 over 4 to the n ln of 4, which goes to 0. You could use the same exact reasoning. If that were a 6, this still would have worked. In other words, this guy goes to 0 and this guy goes to 0. And so our limit becomes 1 times 1, which is 1, which is greater than 0 and finite. So by the limit comparison test, this series and this series behave similarly. Of course, we're not done because we have to say what Bn does. So what could we say about Bn? I know we've been using p-series a lot lately, but this is not a p-series. We have 4 to the n over 6 to the n. This is actually equal to 4 over 6 to the n. What kind of series is this? This is a geometric series. The first term, if you plug in n equals 1, is 4 over 6. And the ratio is 4/6, and that's less than 1. So what can we say? This means that it converges. Now notice I could tell you exactly what it converges to because it is geometric, but we don't care because that doesn't mean that we're going to know what an converges to. Just because Bn converges to a number, it doesn't mean an converges to the same number. The theorem just says that they behave similarly, right? Okay, so Bn converges. And remember, we've already said that they behave similarly here, right? That was our conclusion. And so, coming back over here, this implies that An also converges. Using this test requires a lot of practice. Using both these tests, right? Comparison and limit comparison test. Make sure you do lots of practice problems where you make sure that the reasoning you're doing is actually correct. You're not just coming up with the correct answer of converge or diverge. Thanks very much for watching this video. I hope it was helpful.